Friends, very good morning to everyone. We were dealing with the disconnection approach of the molecules which are containing two parts and are connected through an heteroatom. When there is a molecule with two parts connected with the heteroatom, we will break the molecule adjacent to the heteroatom. And to get those synthons, we use the reagents responsible for that particular synthons. Further, we have dealt with the chemoselectivity problem. Whenever there is two functional groups and are equally reactive, and we have to make only one group reactive, another to be left unreactive, we should selectively choose the reaction condition such that only one of the functional group reacts. When this is not possible, then we will protect the functional group which we do not want to react and then make the reaction to occur, and further afterwards we deprotect it. Though it increases two steps. One step is the protection step, another after completion of the reaction, the deprotection step, when there is no alternative for choosing a particular reaction conditions such that only one functional group is made to react, we go for this protection. Today's subject of discussion is two group CX disconnection. In the previous examples, we had seen when the two parts are connected through an heteroatom, we disconnect adjacent to the heteroatom. Here a situation is there in the molecule in which it has two functional group attached to the carbon. Then we do CX disconnection. If they are 1,1 difunctionalized compound, means the two functional groups are attached to the same carbon, it gives 1,1 difunctionalized compound. For example, I can take this kind of molecule. Here there are two functional groups, ether linkages, attached to the same carbon. This size is 1,1 difunctionalized compound. In this case also, we break the molecule over here and we also break the molecule over here. When I bracket both the points, then I represent it as 1,1 dihetero disconnection. 1,1 disconnection in the simplest form. If I break over here, this part I'll get is a 1,2-diol. And here I add a functional group, that is carbonyl. The lone pair of electrons on the oxygen attacks on the carbonyl carbon. Pi electrons moves onto the oxygen over here to maintain its tetravalency. It becomes OH. In the presence of acid, again OH becomes OH2 plus. To satisfy this OH2 plus, the bond between the carbon and oxygen breaks, and that electrons are utilized by oxygen and creating a positive center on this carbon. Another OH reacts and OH gets kicked off. I will get the diether linkage compound. Another example of 1,1 difunctionalized is an amino acid. It has amino group and carboxylic group, difunctional group attached to the single carbon. That's why it has become 1,1 difunctionalized compound. COH is a weak electrophile. That's why we cannot attach directly. Hence, I will replace it by the another function group. I'll carry out functional group interconversion. The COH can be replaced by another functional group cyano. If cyano is there, CN minus, it is a nucleophile, it can be attached more easily. Cyano, if I carry out hydrolysis in the presence of concentrated sulfuric acid, that is acidic hydrolysis, the cyano group hydrolyzes to carboxylic acid group. Right. Now I will cut over here and cut over here. 1 comma 1 disconnection I'll carry out. When I cut over here, this part I can replace it by ammonia. The Cn minus I can replace it by HCN, and like I added the carbonyl group over here, I added the carbonyl group to the RCH. The aldehyde reacts with ammonia to give an imine, and the imine formed reacts with hydrogen cyanide to give the corresponding amino acid, and this has been used in the Strecker synthesis. Now you can appreciate the strategy of 1 comma 1 disconnection. In case of synthesizing 1 comma 1 difunctionalized compounds. Similarly, one more example I can give. Here it has the OH and CH2NH2. This is actually the first position, there is one functional group. At the second position, it is another functional group, amino group over here. It is actually 1 comma 2 difunctionalized compound. In this case, this CH2NH2, I replace it by cyano. Cyano group, I reduce it by using a suitable reducing agent, while this Ca triple bond N gets converted into CH2NH2. I do 1 comma 1 disconnection. I break it over here between the carbon and cyano. I'll get Cn minus. Cn minus is the donor synthon. As this gains the negative charge, the electrons are moved towards here. The cyclohexyl group gets the positive charge. This acts as an acceptor synthon. Now, the reagents used for this donor synthon and acceptor synthons can be a cyclohexanone. I want a positive center over here. That's why I use a carbonyl oxygen. If it is electronegative, this will be slightly positive. This, because of the electronegativity of the oxygen, it renders the adjacent carbon electron deficient. And Cn minus can be obtained from potassium cyanide. K plus Cn minus attack on the carbonyl carbon. Pi electrons moves onto oxygen to maintain its tetravalency, and O minus becomes OH, and I will get the corresponding 1 cyano 1 hydroxy cyclohexane, which upon reduction I can get corresponding cyano group reduced to CH2NH2. This is the strategy followed for synthesizing 1 comma 1 difunctionalized compounds. Opposite to that is the retrosynthesis. I'll break up at the heteroatom junction. That's why we call it as 1 comma 1 disconnection approach. If the two functional groups here in this case they are present at 1 and 2 position, then they are 1 comma 2 difunctionalized compound. The 1 comma 2 difunctional compound, I'll convert it to 1 comma 1 difunctionalized compound, and then I do 1 comma 1 disconnection. All the times this may not be possible. In that case, what should I do? If they are 1 comma 2 difunctionalized compounds. Here 1 comma 2 difunctional compounds, and in this difunctionalized compound, one of the functional group is alcohol, The another functional group is another nucleophile, and they are at 1 and 2 position. Then what will I do? I'll break over the molecule at the junction where I have an heteroatom. This is 1 comma 2 disconnection. Disconnection has occurred in 1 comma 2 difunctionalized compound. I break over here. This becomes an acceptor synthon. Nr2 minus, it becomes a donor synthon. The reagents which can be chosen for this acceptor synthon and the donor synthons are, this is positive center, oxygen has lone pair of electrons, and this can be shared to satisfy the positive center. When this shared, the bond has been formed between oxygen and the carbon, which is electron deficient in nature. I'll get corresponding epoxide. This epoxide I treat with Nr2. Nr2 dialkyl amine, this has lone pair of electrons. It can attack on the positive center. Carbon oxygen bond breaks and oxygen, the electrons moves towards oxygen and O minus combines with H plus to give OH. And I have synthesized difunctionalized compound at 1 and 2 position. This is the strategy followed for the two group CS to 1 comma 2 difunctionalized compound synthesis. I can explain this further with an example of phenaramidol. It is a muscle relaxant. This is phenaramidol. It has the amino group at first position and the OH group at the second position. That's why it is a 1 comma 2 difunctionalized compound. As I did over here, I broken up the molecule at the amino position adjacent to the amino position. Likewise, I'll also break the molecule over here. I'll get an acceptor synthon with the positive charge and a donor synthon with the negative charge. These important synthons can be replaced by phenyl epoxide and the 2-aminopyridine. The aminopyridine, nitrogen has lone pair of electrons. It can attack over the positive center. The carbon oxygen bond breaks and the excess electrons are moves on to the O, and O minus combines with H plus. I'll get phenaramidol. This is the approach followed for the synthesis of 1 comma 2 difunctionalized compounds. I can give one more example, propranolol, a beta blocker which is used for the treatment of hypertension. Here it has naphthalene ring system to which a side chain is attached. In the side chain, it has amino group and OH group at 1 and 2 position respectively. I'll break over here. When I break over here, this part will isopropyl amine and this part will be an acceptor synthon. It is O plus, this carbon plus and excess electrons on the oxygen. It shares with this plus and I get a corresponding epoxide. If I do 1 comma 2 disconnection, naphthyloxy methyl epoxide. Then the second function, this is also 1 comma 2 functional group. Here this is at one position there is an ether functional and another position is also ether. Then I'll break over here. When I break over here at the adjacent to the heteroatom, that is oxygen, this part becomes the donor synthon O minus. That naphthyl oxy group can be obtained from naphthol, alpha naphthol to be precise. And another part will be C6H5CH2 plus. There is an acceptor synthon. This acceptor synthon can be obtained from the reagent epichlorohydrin. Because of the presence of electron withdrawing group, this carbon is electron deficient, oxygen is electron rich. It attacks on this, and I'll get this corresponding epoxy derivative or naphthyl oxy derivative, which again is treated with isopropylamine. I'll get propranolol. In this, there is 1,2 disconnection approach. If the two groups, functional groups, are present at 1 and 3 position, they are 1,3 difunctionalized compounds. If in case of 1,2 difunctionalized compounds, one of the functional group is carbonyl, we also follow the similar strategy. There, to get the acceptor synthon, we use epoxides. In case of carbonyls, in case of 1,2 5 difunctional compounds in which one of the functional group was OH, to get the acceptor synthon, we use epoxides. If one of the functionalized group is carbonyl oxygen, then what is the approach? Here, one nucleophilic group at one position, at second position, the carbonyl group. This is 1,2 difunctionalized compounds. Here, I'll use the strategy of breaking the molecule next to the heteroatom. The nucleophile will have an heteroatom. 1,2 disconnection. I'll get an acceptor synthon and a donor synthon. Acceptor synthon CH2 plus. To have plus over here, I will add an easy leaving group and an electron withdrawing group like halogen. It creates the positive center. Why this carbon is positive? Because it is flanked between two electron withdrawing groups. One is halogen, another is carbonyl. Carbonyl pulls the electrons towards itself, and halogen also pulls the electron towards itself and makes this carbon electron deficient, a positive center. I can give an example and explain this. Here, it's a 1,2 difunctionalized compound. The second position, there is a imidazole ring system. At the first position, the carbonyl group. I'll break adjacent to the heteroatom. I'll get a acceptor synthon over here and a donor synthon, that is imidazole ring system. To get this acceptor synthon, I'll add an electron withdrawing group and an easy leaving group like halogen. I'll get corresponding CH2Cl. The lone pair of electrons on the nitrogen over here attacks on this carbon owing to the positive center. Halogen gets kicked off as it's an easy leaving group, and I'll get the target molecule. If I can also add bromine, the chloro or bromo are highly reactive electrophiles, and this controls the mono versus polyhalogenation. The relative reactivity, if it is methyl chloride, it is 200%. There is no possibility of other molecule polyhalogenation. Isopropyl 0.02 relative reactivity. Allyl chloride, if it is there, it is 80% relatively reactive, K relation, and so on and so forth. If the two groups are at present at 1 and 3 position, the functional groups, and that one of the functional group present is carbonyl. Here you see 1, 2, 3. At third position and first position, there is carbonyl group and a nucleophilic group. Here also we follow the same strategy of disconnecting the molecule adjacent to the heteroatom. I break up over here. 1,3 disconnection occurs. I'll get an acceptor synthon and a donor synthon. This acceptor synthon, which is having positive center at third position, 1, 2, 3, they have two hydrogens. This hydrogen carbon bond breaks, and that electrons are used to satisfy the positive center. I'll get it unsaturation over here. When I create unsaturation here, I'll get alpha beta unsaturated ketone. If R is H, it will be aldehyde. Alpha beta unsaturated carbonyl carbon can be used as a reagent to get this acceptor synthon. I treat with the nucleophile Nu minus. The pi electrons moves towards this carbon, creating the positive center over here, and nucleophile attacks on this positive center. I will get 1, 3 dicarbonyl compound. For synthesizing 1, 3 difunctionalized compound in which one of the functional group is carbonyl, I use alpha beta unsaturated carbonyl functional compounds as reagents. I'll take a part of atropine, which is used as a muscle relaxant. Here you see carbonyl first position, second position, third position there is nitrogen attached to it. I break up over here. 1, 3 disconnection I will carry out. I will get an acceptor synthon and a donor synthon, cyclohexylamine. To get this acceptor synthon, I will add unsaturation over here. I will get corresponding alpha beta unsaturated carbonyl compound. This excess electrons on the nitrogen attack on this carbon and pi electrons moves over here. A Michael addition occurs. In other words, to synthesize 1, 3 difunctionalized compounds, I use Michael addition as the strategy, and this is all about the disconnection approach when it has difunctionalized compound at 1 and 1 position, 1 and 2 position, and 1 and 3 position. If difunctionalized compound, here ether linkage, here amino group 1, 2, 3. At first position oxygen, a functional group. The third position amino functional group. CH2 NH2 is there. When CH2 NH2 is there, I'll replace it by another functional group, as I cannot add CH2 NH2 directly. I do replace it by cyano. Then I have cyano group at second position and oxygen group at first position. It has become 1, 2 difunctionalized compound. I break up the molecule over here. 1, 3 disconnection. This part is the donor synthon O minus. I will use corresponding alcoholic derivative of this cyclic ring system, and here this will be an acceptor synthon. This is the positive center, and I add unsaturation over here. I get alpha beta unsaturated nitrile. The OH minus attack on this and pi electrons moves over here. Michael addition takes place. Here also I use the same strategy of Michael addition to synthesize these kind of molecules. In the next class, we will deal with 1, 1 CC disconnection, 1, 2 CC disconnection, 1, 3 DC disconnection. Till then, have a nice day. Thank you.